Can you work,
Finally, I got a question. Feel real lonely.
can you do 5.1.3?
I sure can. Now, these are gonna be a little more, first, they don't have a solution, so you're gonna have to work with they have the answers. Actually, that's the way I prefer. Because if you have the answers, at least you know where it should be. If you don't get it, you gotta kind of figure it out yourself where you messed up. Anyway, with that in mind, let's start. Go ahead, read the problem.
It says determine the frequency where the resistance of a 20 gauge solid wire
It's 20 gauge, and that's American wire. Go ahead.
begins to increase because of the skin effect.
Okay. Now, this is the one thing. R DC was equal to just L over sigma times pi a squared, right? And then R high frequency, really, is equal to L over sigma. And if you want to be exact, it would be pi times, and then it would be a squared, right, minus the quantity, and would be a minus the skin depth squared. The outer area is pi a squared, but if it's within the skin depth, you're going to say it's within the skin depth of the surface. So if you think about this, if this is radius a, and it's within the skin depth of the surface, what you want is this area right here. Now if this is a skin depth right here, it would be the outer area minus the inner area. Well, the inner area is going to be pi a minus the skin depth squared. Follow? Does that make sense to everybody? Now, usually this is approximated, and this is true when the skin depth is much less than a. This is approximated as just L over sigma pi, and then it's just going to be 2 pi a times the skin depth, or sorry, it's just 2 pi a times the skin depth. That's how it's usually, it's the perimeter. Just think of, cut this thing and turn it straight. It would be the length, 2 pi a times the skin depth. That would be the area, right? But the assumption it's much less. If the skin depth is of the order of the area, then you have to take this one, and that means R high frequency is now going to be equal to L over sigma times pi, and then you're going to have a squared minus the quantity, a squared minus 2a delta plus delta squared. And that's L over sigma pi, and then the a squareds cancel, and you get 2a delta minus delta squared. And this does assume, though, for this case, that delta is less than a. If delta is greater than a, the formula is off, because if delta is greater than a, just think about it. What happens? That means this skin depth is now negative, if you follow me. The skin depth would be more than the allowable area. Follow me, class? So that's what you get. Now, where do the two become comparable? In your book, it's going to say something. If you would plot this right here versus frequency, and if you did it in a log scale, if you did a Bode plot of this, you would see that the resistance would remain flat, and the point where all of a sudden here in frequency, where it would become, let's see, it would be, technically, I think in the book he has this is going to be 2 skin depth over A, and then it's going to start going up at plus 20 dB per decade, and he has a plot of this. Did you all see that, class, in your books? Or, wait a second, Whitworth has this in his book. I'll give you the page. But where he gets it is this. He's going to set this right here. Oops, sorry. This. The pi times, just listen to me and you'll see it, times 2a delta minus delta squared, because that's the area, all right? That's going to be equal to the original area, pi A squared, all right? And it's that divided by the square root of 2. And so, what do you get? So then, actually, we could do this. We can even get rid of that one for now. We could say that that A goes away. Actually, let's select that, and that's gonna be A over 2 delta, or 2 delta over A. Does he have 2 delta over A, is that point in the book?
Yeah.
What he does is he's gonna, I'm sorry, I put it here, should be, he equates this to this area. And that's when it, all of a sudden, it goes out. Here's the real thing about this, if you listen to me. At this point right here, the effective resistance went up by the square root of 2. So the way I always remember this, if this is a real plot, the resistance right here would be the square root of 2 times RDC. And that's the easiest way. So if you want to calculate that frequency, so this is 20 gauge, right? Now I gave you the information about wire, American wire gauge, right, AWG. And so the conductivity is going to be 5.8 times 10 to the 7th, and that's Siemens per meter, 1 over ohm meter. Now the next thing you need is the radius of the wire, or diameter. What's the radius of 20 gauge wire? I don't know.
It says the diameter is 32 millimeters.
All right, so that means it's 16 millimeters is our could use diameter, right?
It's mils, not millimeter.
Yeah.
It's mils?
You have to convert the.
Doggone it, I hate doing expressions. I dislike using conversion. It's 16 mils. And what is that? 2.5. What's the conversion factor he has?
1 mil, no, yeah, 1 mil equals 25.4 micrometers, I think.
Yeah. $25.4 times 10 to the minus 6, right?
Yes, sir.
And that would be micrometers. So what is that going to be? 25 times 16 is
I got 0.4 millimeters.
0.4 millimeters.
Yes, sir.
Anybody else confirm that? And they want they want to know what frequency, right?
What did I get? 0.4?
Pardon?
Yeah, it's 0.406.
Yeah.
So that's
0.4 is okay. Now for this, the next thing we need is the skin depth, and I'm going to put this right here. The skin depth is equal to 1 over the square root of pi f mu sigma. So the skin depth would be equal to. Can you give that to me? Now is this is just regular copper wire, not steel, right?
it didn't say.
It's assumed copper unless it says differently. So if it's copper wire, mu is just mu naught. What do you get for the skin depth? Oh boy, what do I mean? We need the frequency.
Yeah.
Sorry. He says he wants to know the frequency where this takes place. So this is equal to this right here is equal to square root of 2, right? And so that means, look, here's what I'm doing. I'm taking this point right here to be equal to the square root of 2. All right? Are you following me on this, class? Now, I'm doing that because I know that's where it's going to increase by that much, but just bear with me. So if I don't, does he have a value for this there in his book or not?
He says 2 sigma over A would be equal to 1 over square root of pi f mu sigma.
Wait, 2, what page is that?
That's equation 9.4 if you move this stuff around.
On what page?
504.
Hold on for 1 second.
So you can change
Oh yeah, you can say
9.4 around and you would get that. 2 sigma over A equals 1 over square root of pi f mu sigma.
Well, he's got it's 4 over pi mu sigma.
Yeah, it's
Right,
9.5.
yeah.
So that's a straight one, right? But still, he. So
frequency roughly estimated.
Oh, it's actually one, my bad. Sorry. This is actually equal to one right here, pardon me, this is one, right there, this, hold it. So two sigma over A is equal, not F, is equal to one. And that means that sigma, right here, sigma is equal to A over two, and that means the square root of pi F mu sigma is equal to two over A, and that means 4 over A squared, divided by pi mu sigma is F. That's what he has in that equation, right?
Yes.
Alright, he gets it by setting this equal to one, my bad, and this is, I'm sorry about this should be versus F, but this frequency right here is associated with two delta over A equal to one, my bad, I should make that clear. This is where this becomes fact, and that frequency is buried in the actual value of sigma, the equation. So if we got it right here. Jay, it should be that frequency would be equal to 4 over sigma times mu naught times pi times A squared, and A squared would be RW squared, so it would be 0.4 times 10 to the minus 3 squared. And what is the frequency, by the way?
I got 109 kilohertz.
So 4 over sigma mu naught pi 0.4 times 10 to the minus third squared. Is that the answer to the problem?
They got 105.8. I got
What?
109.2.
That's what I got.
This could be a round off error.
That's 5.8 times into the 7, right?
Yeah.
Sigma.
Mm-hmm.
Okay. So then, yeah.
Say again what you got?
109.2 kilohertz.
I don't know if 0.406 would change it that much.
Can try.
I don't think it would, but I mean, I'm just saying, I'm thinking of reasons why it didn't agree exact.
Yep.
It
That
does?
gives me
Yeah.
105.97, so, yeah, if you use 0.046.
What was the answer? Online, it was 105.8 kilohertz.
97.
Yeah, that's it.
Yeah.
That's good enough.
So,
Alright, another question?
let's see.
What's that?
The last question.
Alright, hang on. Alright, go ahead.
Determine the resistance of a 6-inch PCB land of width 5 mils at 1 megahertz and 40 megahertz.
So they got a 6-inch, and it's, the width is 5 mils,
Yes.
and what's the,
1 megahertz.
no, what's the thickness? Oh, they want just in different frequencies they give?
Yeah, they give 2 different frequencies.
Alright, here's why, because now you look at this dimension as simply the skin depth. Alright, that's the idea, because the current's just gonna ride the top surface, alright? So in any case, the resistance of this, let me actually do this. Let me do it this way. This is the real way to do it. He doesn't give you any parameter of height here, any thickness.
It just says PCB land of width 5 mils.
Alright, that means the effects of these edges here and on the other side are negligible. Here's what happens. You're basically gonna carve out one skin depth on the surface there. And you're gonna say all the current is going to reside within 1 skin depth of the surface. All right? Now, first thing to do is calculate the skin depth. And I don't like to work in inches and stuff like this. Can you give me 6 inches in millimeters? So that's what? 2.54 centimeters is equal to 1 inch, right? So that's 6 inches, multiply 2.54 by 6, and that'll give me the number of centimeters this is.
Are you on centimeters or millimeters?
It doesn't matter.
152.4 millimeters.
152.4 millimeters this way, right?
And then
And the width,
0.127.
127 millimeters?
Yep.
Millimeters, all right. Now we've got this, and we're gonna ignore these dimensions here because they're gonna be so small, they're insignificant, all right? Now the next thing we're gonna do, once we have that, is we'll calculate the resistance, and this is assumed copper, right? So conductivity is 5.8 times 10 to the 7th, isn't that right, class? Correct? And here's what you do. Resistance will always be, if you've got a skin depth effect, the resistance will be equal to the length, so it's always proportional to length, inversely proportional to area, and inversely proportional to sigma. It's always gonna be this for something of constant cross-section where the current's flowing down the thing, or it's flowing right through that constant cross-section. Can you all follow me, class? All right, so the length is equal to 152.4 millimeters times 10 to the minus 3. Sigma is 5.8 times 10 to the 7th. And then the area, if you look at the area, right, it's going to be this length, 127 millimeters, or 0.127 millimeters, times this length, because there's 2 of them, right? Right, what I'm gonna do is get this area is gonna be this length plus this length times this thickness. Follow me, class? Just cut this thing and straighten it out. Cut it right here and straighten it out. Ignore these edges, they're too small, right? Can you all see this? All right, so that means the area is gonna be the skin depth that we're gonna get in a second, times 2 times 0.127 millimeters, and that's times 10 to the minus 3. Now the skin depth is equal to 1 over the square root of pi f mu sigma, and f in this case was what?
1 megahertz.
So what's skin depth? Can you give that to me? Can you see it from there? And you can?
You're at 66 micro
Anybody else?
or 66.1.
Micrometers? All right, so that means that goes here. Can you give me the answer for what that resistance is? Anybody? Y'all need to get MathCAD. I see these guys' laptop popped up. MathCAD will do this thing that fast. Put all the constants like mu naught, epsilon naught, C, sigma copper. Just put them at the top.
156.5
Ohms?
milliohms.
Okay. 156.5 milliohms. Is that the answer in the book, or the answer?
They got 0.59, so 590 milliohms.
They got 590 milliohms?
Yeah.
Let me see this problem. There's no way we could be that far off. Is that length right, 6 inch long?
What is this?
Which one is it?
That one at the bottom.
It says determine a 6 inch check on Google is
That's,
six?
I Googled,
That's it?
yeah, I Googled both of those.
That's right, and this is right? Point
That was
Yeah.
on Google.
127?
I calculated.
Yeah.
Alright, is this right?
That's what I got.
Alright, now hold on. Then this has got, this 152.4 times 10 to the minus third over 5.8 times 10 to the seventh, right? Then it's times 2 here, right? Times the skin depth, which is 66.1 times 10 to the minus 6, times 0.127 times 10 to the minus third, and you're saying this is what we get?
That's what I got.
Alright, well, because that's so far out of whack, I'm gonna see what I get. Cause something doesn't sound right. I got MathCAD right here too. Where's skin depth? I agree with you about your skin depth. I got 0.157.
That's what we got.
Let me check one thing. I could believe maybe it's wrong, but it seems way out of base. They're really bad. Just hold on for 1 second, I wanna see what the problem is. Cause that should work.
I think it might be a different signal.
That's what I
Well,
was thinking.
it say copper?
It didn't say anything.
It don't state on
None of the
like any of the
problems say
problems.
It gives you a frequency though, so you could like backtrack it and solve for sigma first.
Well, you could, but that should be said explicitly. PCB is almost always copper.
Yeah. It's cool.
Hold on for 1 second now.
Fancy.
which problem is that again?
This is 5.1.6. When we get skin depth from Sigma, it's just the Sigma was smaller. Sigma was smaller, where skin depth is bigger. I don't see how skin depth is gonna change it that much though, because it's inversely proportional to skin depth, which will make the skin depth bigger if it's smaller, but it being smaller than the current answer.
Well, that's problem 5.what again?
Point, it says 5.1.6.
Yeah. We got the right form, we're doing everything right. That's just
Yeah, I can't.
the answer's wrong. I'm just telling you that's, everything we've got there, the formula, or I would just look at the book I got it from. It's just this perimeter, and you ignore this effect, that you have to worry about is the area. I mean, I'm assuming that this is right. The only thing I'm thinking about, I keep thinking in the back of my mind, 6 inches in mils, right? Or 6 inches. That'd be 6 inches times 2.54, that would put it in centimeters. So 6 times 2.54. Does that give 152? All right. And the width is 5 mils, right? And 5 mils converts to 0.127, is that right? Millimeters? I just gotta make sure about this, because usually that book is not that far off. Is that what you got?
Yes, sir.
Then I'm gonna tell you the answer is wrong, because this is right. That checks out every box. So my bad if I didn't check that one first. But then the other answer is gonna be wrong too, because now when we take it to 40 megahertz, right? Is it 40 meg?
Yes, sir.
Well, here's what's gonna happen. Now the skin depth at 40 megahertz, when F is equal to 40 megahertz, now the skin depth is gonna be much less. And what does it come out to be? It's the same formula. The only thing that you're gonna do is change the skin depth.
Get 0.9899, so 0.99.
.99 microns?
0.99 ohms.
Oh, for this.
Yeah.
Right. The only thing I can think of is he's talking about, if you're thinking about running this in a differential mode, it could be twice this, but twice this only brings it a little over 300 milliohms. And his answer is 0.509, right?
You got 0.59 and then 0.776.
Wait a second, it's much bigger than the second one. 509 and then 7 point.
0.59 and 0.776. Whereas we got 0.1.
At 40 megahertz.
Yeah.
It's something, it should be
That
much
didn't-
greater.
That didn't move a lot.
Well, go ahead and take a look at ours. Take a look at ours. This is at 1 megahertz, right?
At 1 megahertz, we got 0.157.
All right, and what do we get at 40?
I got 0.99.
Yeah, which is about it's really 990. It's a factor of about, what, 7 difference than this? It should be that too. There's something wrong with those answers.
If you take the answer and go backwards through the equation, you get a conductivity of about 4 times 10 to the 6.
See, aluminum, copper, gold, silver, those are all times 10 to the 7th.
Yeah.
So getting down to 10 to the 6th,
It could be made of lead.
no.
That's
Stainless
the
maybe, if
closest
it's
thing
stainless
on the
steel,
table.
your permeability becomes,
Stainless
relative
steel
is
is
1,000,
1.1.
huh? What's that?
Stainless steel is 1.1 times 10 to the 6.
For what?
So you can
yeah, but mu relative is gonna be 1,000.
Yeah.
That's the thing. I tell you what, let's not spend any more time on that. That answer's misleading. This is how it should be. Do you have other questions? Hmm? Go ahead.
Oh. You can do the first one.
Okay.
Let's calculate the per unit length DC resistance of the following wires.
Well, that's pretty simple.
Yeah.
RDC is just straightforward, length over sigma A, find the cross section. That's a no-brainer, but
Yeah.
is
And
there
then
another?
the other ones are just like that first one we did. So.
All right, so are we good on this? It's always the area that is associated with the skin depth that you have to worry about.
You can do the inductance one. if you want.
Okay, which one is it?
It says determine resistance, internal inductance, and external inductance, and capacitance of a typical ribbon cable consisting of number 28.
All right, hold on. Let me draw this up. Oh, we're talking about per meter parameters, right? Right?
It just wants resistance, inductance.
Yeah, but it's per meter, it can't be, because of the cable that has to have a length. And give me the spacing on this one. It's a ribbon cable, what's the spacing?
The cable consisting of two number 28 wires, 2 meters in length and separated by 50 mils.
Number 28 gauge,
Yeah.
and that's American wire gauge. And,
2 meters long.
how long?
2 meters.
Oh, they want 2 meters long. All right, and,
50 mils apart.
50 mils apart, and now we gotta find the radius of these wires. What we need to do is find this radius right here, or diameter. And so that's number 28 wire. Can you look it up and give me the diameter of that in mils?
28 is 12.6.
12.6.
Wait. I believe so. That's very solid.
Yeah, well, this is solid.
Yeah.
12.6, go ahead.
That's mils.
In mils,
That's the diameter.
so I take and multiply that by 25.4 to get it in microns if I wanted it, and then divide by 2. So let's just take this times 25.4, mils cancel mils, I get micrometers, and then I divide it by 2. So that means the radius is equal to, what, 12.6 divided by 2 is 6.3 times 25.4 times 10 to the minus 6. Can you just give me that?
It should be 0.16 millimeters
16 millimeters?
for the radius, correct?
Yeah.
Yeah.
All right. If that's the radius, now here we have to know that this is the radius here. That's the radius here. And now we're going to start. They want external inductance first or internal?
They want resistance first.
All right, resistance. At what frequency? Oh, just DC?
100 megahertz.
F equals 100 megahertz. So now we have to find skin depth. That's equal to 1 over the square root of pi f mu sigma. And again, sigma is 5.8 times 10 to the 7th, right? So what do you first get for the skin depth at 100 megahertz?
You got 6.6 micrometers.
Anybody confirm that?
0.61.
Micrometers?
Yeah.
All right. Skin depth. So that means if we're going to talk about the resistance, now RDC, you got to understand there's 2 wires, class. So they're talking about differential mode. Current comes, unless they're attached in parallel, but does it say anything about the mode they're driven in?
Just says a typical ribbon cable.
Then it's driven differential. That means current's going down one and up the other. It's returning. It's like an extension cord. So RDC is going to be 2. not DC, but high frequency. Well, first of all, this is gonna be the skin depth. Now take a look at this. This is the radius, all right? That's millimeters, right? So it's 1, 2, 3, it's 160 microns. So obviously the skin depth is much, much less than the actual radius of the wire. Agree, class? So we can make the case skin depth is, A is much, much greater than skin depth. Therefore, the resistance, and that's the high frequency resistance, and it's for both wires, would be 2, and then it's gonna be times the length, which is 2 meters. So it's 2 times the length divided by sigma, which is 5.8 times 10 to the 7th, and divided by the cross-sectional area. Now here we just use the perimeter times the skin depth. So here it becomes times 2 pi, radius of the wire is 0.16 millimeters times 0.16 times 10 to the minus 3, and then it's times the skin depth, times 6.61 times 10 to the minus 6. And that's gonna be the high frequency resistance. Can you punch that out for me, people?
You're up 10.4.
Anybody else?
I got that too.
What do they have?
3.7.
Wait a second.
I was just kinda close if you think about it.
Wait a second. So just for one wire, it'd be half that, right?
Yeah, well, that's like 5.2.
Yeah, which is bothering me. And what did they get?
They got 3.7. Or 3.74. Makes it a little closer.
Wait a second, is this the right for 28 gauge wire?
28 gauge wire.
12.64 mils.
Would be the diameter.
Divide that by 2.
Right.
That's 6.
Yeah, 0.16 is right.
Yeah. For the radius.
That means the area would be pi RW squared. Give me that number.
Uh, 8 times 10 to the minus 8.
8.04.
Yeah.
This is copper, right?
None of
It
them
doesn't say.
None of them say.
Yeah, that's the default. If it doesn't say copper, you always use copper, right? Then for this one, the actual resistance should be the length, L over sigma A, and that's the cross-sectional area that the current would flow through. The length is 2 meters. Sigma is 5.8 times 10 to the 7th, right?
Yeah.
Then it's the times the cross-sectional area, which is 8, right? Times 10 to the minus 8.04 times 10 to the minus 8, right? Is that right? Yeah. Now that's just for one wire. What do you get for that? Just tell me that.
0.43.
0.43.
3.
Ohms. And they got 0.3.
I think it's stranded wire.
Yeah, big stranded wire.
Ah!
Because it says AW7 by 6.
Yes, 7 is the number of strands. Oh, it's not solid. Okay, never mind.
Okay.
Mystery solved. Now here's what we got. all those things for skin depth and stuff still take, they're correct, but here's what happens, when you have stranded wire, you have this.
So it's.
You got a bunch of small balls, or think about a bunch of strands of wire all wrapped with resistance, so it's 7 by how many? 36? Alright, now each one of these wires, that means there's 7 number 36 gauge wires in there. You follow me on this, class? They're not 28 gauge, they're 36 gauge wires, but there's 7 of them. You follow me?
Yes, sir.
Now you go to 36 gauge, now we're gonna get this. Fine. Go to 36 gauge and give me the radius or the diameter in mils. All these are in parallel, so I'll show you how to do this one. This is actually a good problem. This is gonna be 7 by 36. This is the gauge right here. So it's 28 gauge stranded wire. And this should be stranded. Does it say that?
Did you say you want the diameter or the
Of
radius?
36 gauge wire.
The diameter is.
Or radius would be fine.
63.5 micro.
63.5 micrometers is the radius. Now the area, which is pi times RW squared. What do you get for that?
1.27 times 10 to the minus 8.
Is that right? Class?
Yeah.
Alright, that's meters squared. Alright, now, here's the deal. Each one of these wires is parallel, right? They're all parallel. So we do just one wire and then we're gonna divide by 7 to calculate the resistance. But then we have to take the proportionates of the length. There's 2 meters one way, 2 meters the other, so it'll be times 4. But first, for one wire, we also have to do this. We've gotta make sure this is still true. So is the radius of the wire, is the skin depth. So now we calculate, what's the first frequency we wanted at? Class?
100 megahertz.
If it's 100 megahertz, the skin depth for 100 megahertz was what again?
6.61 micrometers.
Now, I'm gonna show you something. That's still much less than this. It's a factor of 10, all right? So because of that, now per wire, this is gonna be per wire, per meter, we get a resistance, that's a high frequency resistance, equal to, and it's going to be, just gonna be per meter, so it's 1 over sigma, which is 5.8 times 10 to the 7th, and then it's gonna be times the area, and the area would be times 2 pi times the skin depth, which is 6.61, times the actual radius of the wire, which is 63.5 times 10 to the minus 6. So could you give me the resistance, the high frequency resistance of a single strand of that for 1 meter of it?
Got 6.5.
Times what?
Just 6.5 ohms.
Y'all get that?
Yep.
Alright, is that right, 6.5? So it's 6.5 ohms, I'm gonna go with you. So it's 6.5 ohms per wire. Now, think about this. One wire would have a total length of 2 meters this way, right? But then there's a return 2 meters. And there are 6 of them, right? And they're in parallel. So the easiest way to do this is take this divided by 6. So take R high frequency of one wire divided by 6, because they're all in parallel. And that would be R of the wire per meter, right? So what do you get for that?
1.09.
0.109? Is that what you guys get?
1.09.
Right? That's per meter. You said it's 2 meters long?
Yeah.
Alright, so if it's 2 meters long, it would be this 2 meters times 2 and times 2 again, so it should be 4 something, and you say he got 3?
3.74.
Alright, well, just take this right here, right, and multiply 1.09 by 4, and that should be the resistance.
Shouldn't it be divided by 7, not 6? Is it
Ah,
somewhere?
7, that's right,
So that was-
7, my bad, 7, what do you get for that then? My bad.
Then it comes out to 3.7.
What is this value right here?
0.93.
0.93, and then 0.93 by 4 is
3.72.
3.72 ohms. And what does he get?
3.74.
I'm gonna say it's
I got
round off
3.
there. Huh?
I got 3.74.
It's just rounding.
Yeah.
Yeah.
You got 3.7. Y'all see that? Now, the next thing they want is what? The inductance? Internal inductance, right? Now I want you to understand this. Inductors in parallel, all right, are like resistors in parallel. The total inductance is half. You understand that, class? And we have, so what we're gonna do is calculate the inductance of 1 wire per meter, all right? And divide it by 7, because there are 7 of them. Are you with me? But this is a high frequency inductance. Do y'all remember this? So for high frequency inductance, and the reason this is, that we can assume this is because the skin depth is much less than the radius of the wire, and that is not the stranded, I mean, not all the strands, 28 gauge, but 36 gauge, all right? So it's much less than this. Agreed, everyone? Work with me on this one. So that means, therefore, the inductance, and this is gonna be high frequency inductance, is the inductance, the DC inductance, this is gonna be internal, by the way, internal inductance. DC, and then it's gonna be 2 times the skin depth over A, and that's a formula in the book. So that's mu 0 over 8 pi, and then it's gonna be times 2 times the skin depth, and the frequency is 6.61 times 10 to the minus 6 divided by the radius, which is 63.5. So give me L, high frequency, and this is only 1 wire, right, per meter. Right, this is just 1 wire. We're talking about the per meter inductance of 1 wire, correct? Not all 7. What do you get for it, guys? Did you get it?
I got 1.04 times 10 to the minus
1.04 times 10 to the minus 8 henries. Anybody else? You guys, anybody else confirm that? Anyone? I want to make sure we're going with a certain calculation. I appreciate calculating too. This is DC right here. I put this off to the side. You're going to use that over and over again anyway.
I got what he got.
All right, we'll go with it. That's 1 wire per meter, right? We have 7, so that means per meter, the total internal inductance, and this is going to be internal. The internal inductance, not external inductance at high frequency, is going to be this. I'll call it LHF divided by 7. So if you take 104 times 10 to the minus 8 and divide it by 7, what do you get?
1.49 nanohenries.
Nanohenries. And therefore, the total inductance internal would be that and times 4, right? Because we got 2 meters one way, 2 meters another way. So if we take 4 times that, what do you get?
5.95 nanohenries.
9.5 nanohenries. That matched our answer?
Yes, sir.
Okay, that's how you get that. What's the next thing I want?
External.
Okay, now this one I'm going to show you. I'm going to have to erase this, so you're going to have to hopefully keep that down. All right, when we talk about the external inductance, here's the one thing you have to understand. Inductance calculations can be done with either energy or flux linkage. You remember that from back before? When you had your electromagnetics course 1, Well, look, the flux is all per meter flux. This is 2 meters, so we actually have to be careful, it's 2 meters. But we have to find all the flux that's penetrating that area between the wires, and then we divide it by the current causing that. Follow me? So you're gonna assume a current's flowing down this way and up this way. Now, if the current's flowing down or up this way, you can see that the flux is coming out of the board. Can you all see that? The B field's coming out of the board from this current conductor. Do you agree? From this current conductor, it's coming out of the board too. So they're additive. The flux is additive. And I'm gonna make this statement. If I assume this is the z-axis and this is infinitely long, and we'll call this distance rho, then I can say that the B field right here, well, it's actually coming out of the board. The B field right here, coming out of the board, can be given as simply mu I, because that's I, over 2 pi rho, and it would be coming out in the minus a phi direction, so it's coming out of the board. That would be the B field. Do you follow me? If I take that and integrate it, and this is going to be the flux caused by, and I'll call this member 1 and member 2 here. The magnetic flux caused by member 1 would be equal to the integral of B dot ds, or it would be mu I over 2 pi rho minus a phi, and the differential surface would be dz d rho a phi. And here's one thing I'm going to tell you. When you're calculating flux, the net amount of flux coming out, if they're both adding, you can get rid of the negative sign, because really inductance is never going to be negative. The way we take care of that is we use a dot terminal convention that I'm going to get to on the transformers to show which way the fluxes are going to link between things. But for this, if we take a look at this a phi dot a phi is 1. Now dz goes from 0 to 2, right? And it should be rho. D rho would go from the radius, call it r wire, right, all the way up to 50 mils, right, minus r wire. Y'all follow me? It's going to start right here. This is the external, and you have to integrate all the way to here. How far is that? Well, that's going to be 50 mils minus the radius. Do y'all see that? So what does this come out to be? That means the total flux caused through there from the first one is going to be 2. When I integrate dz, I just pull a 2 out, and then it's mu I over 2 pi. When I integrate rho, 1 over rho, d rho, I get natural log, so I get this times the natural log, and it's going to be from 50 mils minus RW. Do you remember RW in mils?
RW in mils?
The radius of the wire. Or you could just leave it 50 mils minus RW over RW, right? And that's the total flux just caused by this current from here flowing. I mean, it's the flux from this current going in here. And I'm going to make the argument, because of similarities and symmetry, that would be the same amount of flux as caused by this current in this direction. Do y'all see this, class? They're literally identical, right? So you can just take this and multiply it by 2 to get the total flux, and then divide it by I to get the current. And so this would be the actual L external. The thing we have to do is take that 50 mils and convert it to,
It's 1.27 millimeters.
thank you. So this is 1.27 millimeters minus R of the wire divided by R of the wire. So what does this come out to be for the L external? It's 2, forget I, it cancels. So it's going to be 2 times 2 is 4, divided by 2 is just left with 2. So we got 2 mu over pi natural log of that. Everybody get it?
at 2.35 micrograms. 2.36 actually.
Microhenries?
Yeah.
What does the book say?
1.5.
1.5. This is external? That's 2 meters, right? Oh, you know what the problem is? We just gotta use the 28 gauge radius. I'm sorry, I'm using 36 gauge. Remember there's 7 of them bundled? Alright, we gotta start out a little further because remember they're all bundled together. That's my fault for not catching. This should be the radius associated with 28 gauge wire. And I don't know what that is, but we had it at the
Is
beginning.
that for solid?
12.6.
12.6.
No, it's gonna be for the 28 gauge brand stranded.
It's 15 mil diameter, so.
15 mil?
Yeah, so.
Perfect, 'cause this is gonna be- Look, this is 50, so it's just gonna be 50 mils minus 15, right? Over 15. Now the calculation is straightforward. Now we should
But
get
it's a 7.5 radius, right? 15 diameter.
sorry, I'm thinking right. 7.5, thank you so much. Is that what you guys, alright, see what you get, 2 times 2, well, really, 2 times 2, divided by 2 is just 2 times mu over pi, natural log, or whatever that is, what do you get?
Which is, they have 1.5.
Close enough. 1.4
Microhenries.
microhenries, okay, that sounds right. Is that it for that problem?
Capacitance.
Okay, capacitance, how do we get capacitance? It's good we're doing this, in a way it's a good review of electrostatics. And it also may, I'm gonna level with you, when you get in the real world and you start doing EMC stuff, if you're in a small company especially, you're gonna be a jack of all trades. I'm just gonna tell you that. My wife's in one of them right now. You might be programming microcontrollers one day, get it all up to speed, next day you're trying to build a circuit and you gotta go through the right wire and all that stuff. So all these things it crops up in front of you. You're gonna have techs that, do the assembly, but usually the engineers get stuck with taking care of everything else. And it can be almost anything too. All right, now how do you get capacitance for any 2-wire system? Let's do it this way. For any system, if you gotta assume something. Let's assume this is infinitely long for now, right? It's still 50 mil, it's separated, the centers are separated by 50 mils, right? And the diameter is 15, so the radius here is still 7.5 mils, right? And we want capacitance. Do you remember the standard way to get capacitances? I'll give you my take on it. You assume something. Usually you assume Q. All right? So in this case, it's not really Q per se. It's a certain amount of charge, but it's going to be rho L because we have long wires. So we're going to assume plus rho L here, rho L, and minus rho L here. All right, so this would be minus. Y'all follow me? It's just like capacitor plates. You got to put wherever plus is, you have to have a minus. Now the next thing you do is you calculate the electric field from this. Now take a look at this and you got to be careful you watch me on this one. If I use this as the z-axis, right? And I'm just going to call that 50 mils W for now so you see what I'm doing. Then I can say that the electric field out at this point, at a point rho away from the center here. Now listen to what I'm saying. The electric field from an infinitely long wire is given as rho L, the charge per unit length, over 2 pi epsilon naught, right? And then it's divided by the distance from there. And in this case, the electric field will be in the positive rho direction. And that's the electric field just from this positive. You all see this, class? I'm trying to get the electric field right at this point. Agreed? Now there's a second electric field, and it comes from here, right? If I come over this way, I'm also gonna have an electric field. The electric field from this one is in this direction. The electric field, this is negative, the electric field's gonna be pointed at. From this one is in that direction. Do y'all see that? With me, class? Because I'm talking about this distance now. And that distance is W minus rho, isn't it? Y'all see it? So all I have to do is say now it's gonna be plus rho L A rho over 2 pi epsilon naught, but now it's W minus rho. Agreed? Then I'm gonna get the voltage. Now just listen. I'm gonna say the voltage will be equal to the integral of E dot dl, and it would go from the inner radius, which is 7.5 mils, to the outer, all the way over to W minus 7.5. So it's W minus 7.5. But here's the one thing I'm going to tell you is a secret. I'm going to contend when I do this integration, it'll look like this. It will look like the integral of rho L over 2 pi epsilon naught rho A rho dot A rho D rho. That's the first part. That's this one from 7.5 mils to W minus 7.5 mils, plus the integral from 7.5 mils to W minus 7.5 mils of rho L over 2 pi epsilon naught. And then it's W minus rho, D rho, A rho dot A rho D rho. But listen to me carefully. Most of you can see this. Same magnitude per unit length charge there is here, right? I'm going to contend that the integral of the electric field from this one, from this point to this point, will be identical to the integral of the electric field from this one, from this point to this point, because of symmetry. Do you all see this? So I don't even bother with that second integral. The only thing I do is get rid of it, and I multiply the first integral by 2, and I say that that in fact will be my voltage. I multiply it by 2, and that's V. And that means it comes out to be what? It's going to be 1 over 2 pi epsilon naught times 2, right? And then it's going to be times the 1 over rho integrated is natural log, right? Natural log of W, which is 15, or I'm sorry, it's 50, right? 50 minus 7.5 over 7.5. The mils cancel. And that should be the voltage. Do you agree with me, class? Now, once you have the voltage, remember there's a rho L there too. To get the capacitance, capacitance is Q over V. So capacitance, when I take Q, which is rho L, divided by that, you'll notice the 2's cancel, and then I get pi epsilon naught, right, divided by the natural log of 50 minus 7.5 over 7.5, and that should be the capacitance. I want to tell you one thing. This formula basically is something that's common for 2 wires. The capacitance per meter is this. All right? But we actually have a 2 meter section. So give me this value right here.
Was it C equals, what's on, for the
Here, I'll put it up
equation?
here. C in general, this is per meter for 2 wires, is going to be equal to pi times epsilon naught over the natural log of the separation of the wires minus the radius of the wires over the radius of the wires. That's the way it is per meter all the time. And for our special case, what is it? Well, it's 50 minus 7.5 over 7.5, right? You gotta take the log. It's natural log, not log base 10, by the way.
I got 0.16 picofarads.
Anybody else? Now that's per meter, right? So it's 0.16 picofarad. Picofarad per meter. There's 2 meters, multiplied by 2. So did they get a capacitance of 0.32 picofarads?
They got 29. I got 32. Yeah, I would get 32 pico.
Alright, I'm gonna level with you.
It should be 16 pico, not 116.
Yeah, it is.
Oh,
16.
16 picofarads.
So 32 and 29.2.
Hmm?
We got 32, they got 29.28.
Alright, I'm gonna level with you. Take out that RC. This is an approximation. If W's large compared to RC, they just get rid of it. See what you get now. It's 50 over 7.5. Take the log of that.
$14.7 pico.
Yep.
Times 2.
That gives me 29.3, and they
Yeah.
got 29.28.
I'm gonna tell you that's an approximation though. Normally you want to have that other, it's this, you know, honestly, Jennifer, I'm level with you guys. If the frequencies they're talking about, just the stray effects of capacitance and really the non-homogeneous, typically wire doesn't have an exact diameter. It gets little undulations, little changes and stuff like this. And a couple of percentage off is something to be expected at these frequencies. You're never going to get it exact. Follow me? You're going to be in the ballpark, close, probably within 10% for sure, within 5 likely, within 2, no, I'm not buying. All right, these are all good problems in a way. It's a good electrostatics review.
Got another question to it.
What's that?
What's the characteristic impedance too?
All right, you know how to get characteristic impedance, people? That's Z0, right?
Yeah.
So it says if it's being used as a transmission line, and it's got to be greater than 1/10 of a wavelength long. I'm going to assume it is. Characteristic impedance is just what? Square root of
Oof.
L over C. Do y'all remember this? Right? Square root of L over C. That's what it is. Like when you see 50 ohm line, it means the square root of the inductance per meter divided by the capacitance per meter is that. Did you remember this at all? Something?
I just remember with the resistance and the impedance or whatever.
Well, typically it was be what? R plus J omega L over G plus J omega C, but R and G you throw out because if you got losses that affect this value, you got a problem. So what is this? The L itself is going to be what? It's going to be both internal and external for 2 meters, right? Can't be just one. So you got to add them up. You're going to say it's L internal plus L external, and it's divided by C. We just calculated C. That would be Z0. What do you get when you do this? I did not expect to take the whole period doing this stuff, but it's a good review for electrostatics, and also we uncovered some typical problems about reading things. 7 by 36 gauge wire, that was the one that got me. But still, it's a mystery to me how they got that land problem. I mean, that piece of deep.
219 ohms.
219, what do they have?
227.7.
227?
It's cause one of our inductances was a little off of theirs. We got like 1.4 and they had 1.5 something.
That's not good. You said 229?
I had 219, they had 227.
Well, see, that's, I know, what is that? That's over 1%, right?
That's 8. Yeah.
Close to 1%. I don't know, but that's the formula, and if you plug in, remember their inductance was off of I could see that. I can see that, but that's the way you do it. You follow me on this class?
Yeah, that's 3% off.
Yeah, that's significant, but that's, just think about what happened. We had 109 versus 104, right? That's the right way to do it. You just make sure you take the prior values, that will get it. We're about out of time. I wanted to just mention, I'm going to tell you where I'm going with this stuff so you know. We got a quiz Friday. It's going to be on something related to this stuff. How's that? But what I'm gonna do is, I'm gonna take care of the high frequency stuff, talk about bandwidth, so I'm gonna go through that, that's what I plan to do today on Friday. This is not in the book, but I will give you very good notes to work with, printed notes like I showed you before. I mean, I've already got some, but we're gonna, it's really gonna be important, you're here this Friday, you take the quiz and be sharp with it. I didn't get much sleep last night. I have a torn, it's called a rhombus muscle, it's below the trapezius muscle, and this thing is just, I was moving some heavy stuff yesterday, and I triggered that thing.
You're not gonna make us convert bills and stuff, are you?
Nah, well, I'll tell you what I'll do.
You give us the converting?
I will allow you to do, y'all have laptops here?
Yeah.
Anybody not have a laptop? Can you read those things on your laptop? I'll give you an open laptop quiz. That means you probably can go to the internet if you want. I don't think it's gonna buy you anything for the type of question I'm gonna ask. Is that fair with everybody?
Yeah.
So, whoever's posting, bring your laptop.
Laptop.
I kinda would like to get all you guys with MathCAD and a few other tools I have, because that way we could do some interesting problems in the next, how many weeks we have left?
Two.
Just two?
I think we were talking about having the test that Monday of the last week. So 2 weeks from the Monday we just had.
Alright, I have to cover, after EMC, I gotta do one thing with microwave, I'll take care of that in short order, alright? And then, hopefully,
That'll be after next week. We go through all next week and have it that Monday after.
yeah, alright. Alright guys, take care of microwave coming up and microwave match. Is it supposed to rain again today?
It's like a 50% chance, but tomorrow I think it's 60 or 70.
Have you been golfing much?
I did this past weekend a lot.
Did you go here?
Now I went back home to my home course.
Well, I gotta tell you something.
They got rid of it, they said it's not gonna rain anymore.
You know it like the back of your hand.
Oh
Yeah, I believe that.
It like
It's a
Those
it's,
days?
yeah,
You
it's
know
like
what,
right
this is
around there.
Alabama.
There's like something about playing your home course. You can I can play awful here, but as soon as I go back home and play my home course, it like everything just clicks.
Tell you, hole three